Okay, so what have we talked about so far in this unit? We've talked about work
Kinetic
and kinetic energy. Do we want to do another kinetic energy example, or do you guys feel pretty confident with kinetic energy?
pretty good.
Pretty good? Okay. So we're gonna start talking then about potential energy. What is potential energy?
Stored energy.
Yeah, stored energy. That's a great way to put it. So potential energy is stored energy. Energy that's stored for later is potential energy. A lot of times we'll call potential energy, we'll abbreviate it as PE. Sometimes you might see it as E sub P. So the first kind of energy that we're going to talk about, oh yeah. Let's see, where's my mouse? Here we go. Okay.
Thank you.
So the first type that we're going to talk about, because we can store energy in different ways, right? So we have different kinds of potential energy. One that you interact with every single day is potential chemical energy, right? Things in your food have chemical energy that give your body energy. But when an apple is just sitting on the table, is it turning into energy? It's stored energy, so it has chemical potential energy. So the first type of energy that we're going to talk about is gravitational potential energy. So gravitational potential energy is going to be stored energy due to gravity. All we need to calculate gravitational potential energy is the work that's required to lift that object. We do the work to lift it up, and then once it's lifted up, that work is transferred into stored energy. So if we have the work required to lift that object up, it's going to be the force times the distance, right? What is the force that we have to overcome because of gravity? If force is mass times acceleration, what is the acceleration? 9.81. So actually, when we're talking about GPE, we can turn this into mass times gravity times height. So your GPE, or your gravitational potential energy, is going to be mass times your gravitational acceleration, which usually is 9.81, times your height. In physical science, a lot of times I'll call this GPE. In our textbook, we can also abbreviate GPE, gravitational potential energy. Sometimes we might say potential energy with a sub G for gravity or a subgravity. Okay. Different people will write it different ways. What are our units? Always, always, always for energy. Joules. Yeah. So our units are still joules. So now we're going to do two examples. So the first one, we're going to find the gravitational potential energy of a 65 kilogram person sitting on a diving board that is 3.0 meters high. How would we start, Brooke? So we could start with that. Would it be a little bit easier to start with our GPE
yeah.
equation? Yeah, so we know that GPE is equal to what three things multiplied together? MGH, mass times gravity times height. So our GPE, you just said it on. Thank you. Our GPE, what is our mass?
65 kg.
65 kilograms. What is gravity?
9.81.
9.81 meters per second squared. What is our height?
3.
3.0 meters. Yes,
Can I get a pass to next?
absolutely. Yeah, thank you. All right, what did we get for an answer?
1,912
1,912. What units?
joules.
Joules, and then if we were gonna do sig figs,
Oh.
how many sig figs? 1900.
I do not like Sig Fig.
I don't like them either. But it's also because we haven't been doing them.
Yeah. All right. So let's do one more example. So a cliff diver drops into water from a height of 46 meters. Holy moly.
Buddy.
His gravitational
it on
potential energy. Oh. His gravitational potential energy decreases by 25,000 joules by the time he hits the water. What is the diver's weight in newtons? How do we start this one?
You do negative 25,000 joules is equal to your mass times gravity times height, and we have our gravity and we have our height. So we just have to find NU times your height by gravity, and then you divide 25,000 joules.
Okay. That would be one way to do it. Yeah, we would say, okay, so if our GPE decreases by 25,000, that means at the top, our GPE has to equal what? 25,000, right?
Yep.
And we know that GPE equals what three things?
That's gravity height.
Mass, gravity, height. So we could say, okay, we know our GPE of 25,000 joules equals, we don't know the mass. We do know gravity of 9.81, or we're assuming gravity is 9.81. And what's the height?
46.
So then we could solve for mass, but that would give us mass in kilograms, right?
Probably. Should.
Yes, it would give us a mass in kilograms. What would we then have to do with that mass in kilograms to turn it into a weight? Nope, we don't have to move the decimals. That would be if we were converting from like kilograms to grams, right? But how do we turn kilograms into newtons? How do we find something's weight? We've done a lot of this. How do we find something's weight? We multiply its mass times what? Yes, mass times gravity. So mass times gravity is going to be weight, right? So do we even have to use this 9.81?
No.
We could say that our 25,000 joules is equal to the weight times 46 meters. This is a force, right? Weight is a force. What is this 46 meters? A distance. So again, we're reinforcing that idea that a GPE is just the amount of work that it takes to put that thing up there. So what is our weight? Let's take 25,000 joules divided by 46 meters.
$543 newtons.
Perfect. What if I wanted to make this a kilonewton? How would I make this a kilonewton?
Move the decimal 3 places
Move the decimal over 3 places. To the left or to the right?
to the left.
To the left. So if I have an imaginary decimal point after the 3, I'm going to take it, I'm going to move it over 1, 2, 3.
0.543 kilonewtons.
Yep. 0.543 kilonewtons.
1400 gigawatts.
Looking at the sig figs in the problem, how many sig figs do each of my numbers in the problem have?
Those ones too.
2. So how many sig figs do I need to round this to?
2.
2, which would make this what?
0.5.
4.
Oh.
Leading zeros are never a sig fig.
Yeah.
If it's in front of the number, it's not a sig fig. If it's a trapped 0, then it is, right? If it's between 2 numbers and trapped. Or if it's a trailing and we have some sort of decimal. So with sig figs, this would be 0.54 kilonewtons. So we now realize that we can rearrange this equation of GPE equals MGH to find different things, right? We can use it to find mass, we can use it to find gravity, we can use it to find height. We can use it to find GPE. We have 4 variables. As long as we have 3 of them, we can find the 4th missing one, right?
Yeah.
Do we want to do any more practice on gravitational potential energy right now, or do we want to move on? Move on. Okay, so now we're going to talk about another kind of potential energy. We're going to talk about elastic potential energy.
Rubber band.
Elastic materials can have potential energy. Yeah, if I pull back a rubber band and I'm stretching it between my fingers, it has energy that's stored in that rubber band, right? Because as soon as I move one of my fingers, what happens?
Shoots back to its original state.
The rubber band goes flying, right? It takes the stored energy and turns it into kinetic energy. So objects like springs and rubber bands have elastic energy because you distort them or you stretch them or you compress them to store energy. But then as soon as you let go, they return to their original size. So we do work to either compress a spring or to stretch it. And then that work is then stored until we let go, and then the work undoes itself, right? So we call that elastic potential energy. So that would be energy stored in springs or rubber bands. Or basically anything that you can stretch or compress. Thanks, Colin. It's energy stored in distorted, elastic, or stretchy material. So potential energy is stored energy, and we do some kind of work to store that energy, right? So for potential energy, the work that we're doing is lifting it up against gravity. What equation do we know for so work is a force times the distance, right?
Yep.
Can we find the force acting on a spring or an elastic object?
Yeah.
How do we do that? We talked about Hooke's law a while ago, right? What is Hooke's law? Force equals what? Do you remember?
No.
What if I say F equals KX? Does that look familiar at least?
Yeah.
So we have the force equals some sort of spring
The
constant
displacement.
times displacement. But the force itself is not a work. We also have to factor in the displacement twice, right? So this turns into, when we substitute Kx for the force, work equals our spring constant times the displacement, and then I'm
Squared?
just, yes. So we have times x again. So, but then our average force, this is our force when it's fully compressed. How do we average something out?
Initial minus final.
Yeah, and then we divide by 2. So it's going to be 1/2. So we're going to have 1/2 kx squared. So this then turns into the work that we do is how we store that energy. So the potential energy of a spring is going to be equal to 1/2 times the spring constant, which is k, times x squared, and x is the distance of stretch or compression. What kind of units are we going to have for elastic potential energy? Units for energy are always joules. Yep. So let's do another example. So we have a spring with a spring constant of 120 newtons per meter is compressed by 2.3 centimeters. How much potential energy stored in the spring? What is the first thing that sticks out to you about this problem? Is everything in our normal units?
No.
No. Which one isn't in our normal units?
Centimeters.
Centimeters. So what do we need to do with that centimeters?
Move it over 3.
Change it to meters. So to change to meters, if you look at my chart up there, how do we get from centimeters to meters?
2.
We move it over to the left 2. So we take our decimal point and we move it left 1, 2. What do we do with the gap here? Add a 0. So our 2.3 centimeters turns into 0.023 meters. Okay, I'm just going to make a note of that. Now what do we want to do? How do we solve this? So PE spring was 1/2 kx squared. So this equals 1/2. Do we have a k? What does k stand for? K doesn't stand for kinetic in this case. It's Hooke's law, so it stands for our spring constant. Do we have a spring constant somewhere? Yeah, with our spring constant. 120. So that's my K. Do we have an X or a displacement?
2.3. I mean 0.023.
Yeah, 0.023. And then we have to square that. Are we squaring the entire term? No, we are only squaring that 0.023. Yeah, 0.031 joules. Let's do another example. I'm going to ask this time, how far must a spring with a spring constant, this time I'm just going to write spring constant as K, of 85 newtons per meter be stretched to store 0.22 joules of potential energy.
Wait, what's the S word? Oh, be stretch.
Stretched, yep.
What if we do the same thing again?
Yeah, so we could say the PE of our spring, the potential energy of our spring, is going to be equal to 1/2 times K times X squared. What do we know?
We know our spring constant.
We know our spring constant is 85.
And we know our answer, our product,
Yeah, we know the PE of the spring is what?
0.22.
0.22 joules. What are we looking for? How far? How far is going to be our displacement? It's going to be that X. So now let's solve.
Oh, you have to do it on your her iPad.
Yeah, I can do it on my iPad here.
Okay. So we can do. Can't we do 1/2 times 85?
1/2 times 85, which is going to be 42.5.
And then equals 0.22, and then divide.
And then divide both
And then
sides.
Get that square root of that.
Mm-hmm.
Okay, so wait, 1/2 times 85, what did you say it was?
That's going to be
2.5.
42.5, right?
Mhm.
.22 divided by 42.5 is what?
0.005. And then do I have to do the square root?
Yep, so then we would square it both sides.
Brooke, what did you get?
0.005, and then I have to square root it, which equals 0.07.
Calculator. Zero 0.07. What are our units?
Joules. No.
How far?
Oh, meters.
Meters. So how many centimeters would that be?
7.
7, right? We would move the decimal point over 2 to the right. So X is 7 centimeters.
Are we asking for centimeters?
It's just asking how far. You could say 0.07 meters. a lot of times you want,
A non-decimal answer.
yeah. Yep, if you can. Sometimes it'll ask you specifically for units. But it's way easier to imagine 7 centimeters than it is to say 0.7 meters, right? Or 0.07 meters. Okay, so we can either do a couple more problems together, or I have a couple worksheets to help you practice kinetic energy and gravitational potential
I'll
energy.
take the worksheet.
Take the worksheet. All right, I'm gonna stop recording then.
Are you posting that to
Yep.
This one was nice and short, 27 minutes.
the classmates are already on that?
Yep.
See if I can
Got like
actually.
15 minutes.
Okay, so I'm